In this lecture, we are going to discuss about Boolean algebra, and we will be going to cover the Boolean algebra laws. So basically, what is the requirement of Boolean algebra? Boolean algebra that is required for the simplification of the Boolean expression, and when we simplify we reduce the Boolean expression, and the benefit here is we can analyze easily the reduced Boolean expression. So what are the benefits? Like if we have the reduced logic expression, or you can say Boolean expression, so we have the saving of gates, and if there is the saving of gates, the complexity of circuit that is also reduced. And what are the further benefits of reduction in the gates? Like if the gates used in a particular circuit are less, so obviously hardware cost will be less, as well as the heat generated by a chip that will be reduced, and most importantly we get high speed of operation. So these are the benefits of using the Boolean algebra. So in the Boolean algebra we have many laws. So we are going to discuss AND law, OR law, double negation law, commutative law, associative law, distributive law, absorptive law, and the De Morgan's law. So you can say total we have 8 laws or theorems, and further these 8 laws or theorems are divided into total 19 theorems. So we are going to discuss all those. Like first law, that is the AND law. In the AND law total we have 4 theorems. Like if we have variable a and that is multiplied by 0, multiply in the sense we are using AND logic here. So if a is ANDed with value 0, so result here is 0. Then second theorem is if a is ANDed with logic 1, then the result will be a. And third theorem is if a is ANDed with a, then the result is a. And the fourth is if a is ANDed with its complement, then the result is 0. So in the last lecture we have discussed the logic symbol, the Boolean expression, and the truth table of AND gate. We can see here this is the logic symbol of AND gate. Here A and B are inputs and the P is output, and the Boolean expression here is P is equal to A dot B. So this is the truth table we have discussed in the last lecture. Like if A and B are two inputs, so there are total 4 combinations possible. Like A and B can be 0 0, or A and B can be 0 and 1, or A and B can be 1 and 0, or A and B both are 1 1. So if A and B are 0 0, P is 0. For 0 1 combination, again P is 0. For 1 0 combination it is 0, and for 1 1 combination it is 1. So what is the logic behind AND gate? Like if all the inputs are 1, then only the output is 1. In rest all the 3 cases the output here will be 0. So from this logic we have identified that if we are putting B constant, so if we are putting B constant, that can be 0 or that can be 1. So if we are putting B 0, then we get P is equal to 0. We can see here if B is 0, P is 0. Here also B is 0 and the P is 0. So irrespective of A, whatever A we apply, if B is 0, output we get is 0. And if we put B is equal to 1, in that case, you can see if A is 0, P is 0, and if A is 1, P is 1. For these two cases, this case and this case, B is 1. So here A is passed to output. If A is 0, P is 0. If A is 1, P is also 1. So from this logic of AND gate, we can say that if one of the input we are putting 0, then output will be 0. And if one of the input we are putting 1, then the output is same as the another input. And if same variable is multiplied by same variable, like if A is multiplied by A in terms of AND gate, A is ANDed with A, then the result is not A square. Like in mathematics we have A square, but here in the digital logic in the binary, if A is ANDed with A is multiplied with A, then the result here is A. And if A is ANDed with its complement, then the result will be 0. So how we can prove these four theorems? Like we can take value of A as 0 or 1 because A is a single variable. So in binary A can be 0 or A can be 1. So what is A complement? If A is 0, A complement will be 1, and if A is 1, A complement will be 0. Now first we need to check A dot 0. So A dot 0, this is A. So we AND this value with 0. So 0 dot 0 is 0 and 1 dot 0, that is also 0. So we check that A dot 0, the result is 0 irrespective of A. And second theorem is A dot 1 is equal to A. So A dot 1, so we are ANDing this with 1. So 0 ANDed with 1, result is 0, and 1 ANDed with 1, result is 1. So we can check this column, A dot 1 and A both are same. So this is the proof of second theorem. And in the third theorem, A dot A, that is equal to A. So here we are putting A dot A. So A is 0 and 1. If A is 0, that is ANDed with 0, result is 0. And if A is 1, that is ANDed with 1 and result is 1. So A dot A, we can see that is matching with A. So A dot A is A. Let's say we AND A thrice, A dot A dot A. So that is again not A cube. That will remain same as A. So if A is ANDed with A n number of times, the result is again same, that is single time A. And if A is ANDed with A complement, then the result is 0. So we have to see A dot A complement. This is A complement, and these two, 0 ANDed with 1, result is 0, and 1 ANDed with 0, result is again 0. So A dot A complement is equal to 0. And second law, that is the OR law. Under this law again we have four theorems. Like A is odd with 0, result is A. If A is odd with 1, result will be 1. And if A is odd with A, that is not twice of A, that will be single time A. And if A is odd with A complement, result is equal to 1. So in the last lecture we have discussed about OR gate. So this is the logical symbol of OR gate. A and B are input and R is its output. And the relation of R, A and B is R is equal to A plus B. And this is the truth table of OR gate. For the four combinations of A and B, we can see R here. So for 0, 0 combination, R is 0. For 0, 1 combination, R is 1. For 1, 0 combination, R is 1. And for 1, 1 combination, R is again 1. So what is the conclusion here? That if any of the input here is 1, like here B is 1, output is 1. If A is 1, then also output is 1. And if both A and B are 1, then also output is 1. So from this truth table, we can see that if we are putting B as constant, so constant value can be put either 0 or 1. So if we are putting B 0, like in the first case and in the third case, B is 0. So we can see here R is equal to 0 if A is 0 and R is equal to 1 if A is 1. That means R copies A, or you can say A is passed to, this A is passed to output. And let's say if we are putting B as 1. So if B is equal to 1, like second case is there and the fourth case is there. So if A is 0, R is 1, and if A is 1, then also R is 1. So that means A is not passed to output. Instead of passing A, output here is permanently 1. So based on this logic, we can check if A plus 0 is there. So if we are putting one of the input fixed to 0, so we can see that the output is same as another input applied. So that is equal to A. And if another input is fixed to 1, then output is 1 irrespective of applied A. So we can see here if one of the input is fixed to 1, then output will be 1. And if A is added with A, that is not twice of A, that will be A. And if A is added with A thrice, that is not thrice of A, that will be again A. So if A is added with A n number of times, that remains A. And what about A plus A complement? That is equal to 1. So here we can verify these four theorems. We have taken here A complement, here A plus 0. So we can check if A is 0, A complement will be 1. If A is 1, A complement will be 0. So first we check A odd with 0. This is A odd with 0. 0 is odd with 0, result is 0. If 1 is odd with 0, result is 1. So we can see this A odd with 0 is matched with A. So we have result here A. Then A is odd with 1. So this is A. This is odd with 1. So 0 is odd with 1 as well as 1 is also odd with 1. So if 0 is odd with 1, result is 1. And if 1 is odd with 1, result is again 1. So we can see here A odd with 1. The output here is 1 irrespective of A. And if A is odd with A, so if 0 is odd with 0, result is 0, and if 1 is odd with 1, result is 1. So we can see here A is odd with A, that is same as A. And if A is odd with its complement, so 0 is odd with 1, result is 1, and if 1 is odd with 0, result is again 1. So here we have output 1. So in this way, we can verify all the four theorems in the OR law. Then the double negation law. The double negation law says that if we take complement to the complement of any variable, that is equal to true variable. So A complement to the complement to the complement will get cancelled out and we have true variable here. We can verify this theorem as like if A can be 0 or A can be 1. So if we are taking A0, A complement will be 1, and if we are taking A1, A complement will be 0. Now we can take again complement of this. So A complement to the complement, 1 complement will be 0 and 0 complement will be 1. Now we can check A complement to the complement, that is same as A. So in this way we can verify this double negation law. Then next we have commutative law. As per commutative law, we have two theorems. Like we have A odd with B, that is equal to B odd with A. Or A is ANDed with B, that is equal to B is ANDed with A. Similar to mathematics, like if we have addition of two numbers. So if we add number 1 plus number 2 or number 2 plus number 1, result is same. And like if we multiply two numbers, so number 1 is multiplied to number 2 or number 2 is multiplied to number 1, that is same thing. So same way we apply the AND logic and the OR logic in the commutative way. A ANDed with B is equal to B ANDed with A, and A ORed with B, that is equal to B ORed with A, and A ANDed with B, that is equal to B ANDed with A. So we can verify these two theorems like here we have A, here we have B. So A and B can have four combinations 0, 0, 0, 1, 1, 0 and 1, 1. So here we check A or B, here we check B or A, here we check A and B, and here we check B and A. So what is A or B? 0 odd with 0, 0, 0 odd with 1, 1, 1 odd with 0, 1, and 1 odd with 1, that is 1. Now we take B ORing with A, so 0 is odd with 0, 0, 1 is odd with 0, 1, 0 is odd with 1, 1, and 1 is odd with 1, 1. So we check A odd with B, that is equal to B odd with A. And here we check A ANDed with B, 0 is ANDed with 0, 0, 0 is ANDed with 1, again 0, then 1 is ANDed with 0, 0, and 1 is ANDed with 1, that is equal to 1. Now if we check B ANDed with A, so 0 is ANDed with 0, 0, 1 is ANDed with 0, 0, 0 is ANDed with 1, 0, and 1 is ANDed with 1, 1. So we check A ANDed with B, that is equal to B ANDed with A. So in this way we can verify commutative laws. Then next we have associative law. Associative law says that A that is ANDed with ANDing of B and C, that is equal to A ANDed with B, and this AND operation is ANDed with C. So it doesn't matter whether we AND B and C first, then AND with A, or we AND A and B first, then AND it with C. So ANDing operation in three variable, that doesn't matter. We AND any of the two variable first, then with the third variable. Same way ORing also takes place, like if we have to do ORing of three variables, so first we can take ORing of B and C, then OR it with A, or we can go for ORing of A and B first, then OR it with C. So same way we can go for the proof, like A, B and C. Total we have three variables, so total we can have 8 combinations now. 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So we can check here B ANDed with C here. So we can go for B and C ANDing here. Here we can check for A ANDed with B and C. So here we can take ANDing of this column and this column. So here we can check for A and B by taking AND of this and this. And here we can take A and B, take this column that is ANDed with C. So we can check that this particular column A dot B dot C, that is equal to A dot B dot C. So these two are matching. So we have verified the theorem. Same way we can go for B OR with C, and then A is OR with B OR C. We check this column with this column, that is A OR with B, then further OR with C. By taking ORing of A and B first, then take ORing with C further. So we check this column and this column, they are same. So in this way, with the help of truth table, we can verify the associative law. Then next we have distributive law. Distributive law says that A ANDed with ORing of B and C, that is equal to A ANDed with B, that is ORed with A ANDed with C. So same way we can verify this distributive law. We can take A, B, C, three variable with the 8 binary combinations. Here we take ORing of B and C. So ORing of B and C is ANDed with A. Then we take ANDing of A and B, and then ANDing of A and C. Then further ORing of A and B and A and C. So this column and this column we match, these two are same, that is A ANDed with ORing of B and C, and here the ORing of A and B and A and C. So next we have absorptive law. Under this we have total three theorems. So first we have A plus AB, that is equal to A. Then next we have A plus B ANDed with A plus C, that is equal to A plus BC. And third is A plus A complement B, that is equal to A plus B. So first we go for this proof, A plus AB. So A we can take common. So this is 1 plus B. And we know that 1 plus something is equal to 1. This is the OR law we have discussed. So 1 plus B will be 1. So here we have A dot 1, and A dot 1 in the AND law we have seen, that is equal to A. So finally we get the result A plus AB, that is equal to A. Then here we have A plus B into A plus C, that is equal to A plus BC. So here we have A plus B dot A plus C. So we can multiply A with A and A with C, that is as per the distributive law, A dot A plus A dot C. Then we have B dot A plus B dot C. So A dot A, that is as per the AND law. Then we have A dot C. Then B dot A, we can write it as A dot B, that is the commutative law we have discussed. B dot A is equal to A dot B, and here we have B dot C. So here we have A, here we have A, here we have A. So in these three terms we can take A common. If we take A common, here it will be 1, here it will be C, and here it will be B. So here we have plus BC. So A dot 1 plus C plus B. and 1 plus something in the OR law we have seen, that is equal to 1. So we can write it as A dot 1 plus BC, and A dot 1 in the AND law we have seen, that is A. So finally we get the result as A plus BC. So remember it, that is A plus B dot A plus C, that is equal to A plus BC. So next theorem we have A plus A complement B, that is equal to A plus B. So for this theorem we can use this theorem, like this is the form A plus A complement B is the form A plus BC. We can take this as A, this as B, and this as C. So this is the form A plus BC that can be split into two parts, that is A is splitted with B and the A is splitted with C. So A plus C, BC is A plus B into A plus C. Take it as A plus BC. So A plus B and A plus C. So we can write it as A plus A complement dot A plus B. And what is A plus A complement? In the OR law we have discussed, A plus A complement is 1. So 1 dot A plus B, and 1 dot A plus B in the AND law we have seen that 1 dot something will be that particular value, that is A plus B. So in this way we can verify the absorptive laws. Then finally we have the most important law, that is the De Morgan's law or De Morgan's theorem. Here we have two theorems, that is complement of sum, that is equal to product of individual complements, and complement of product is equal to sum of individual complements. Or we can say the complement of OR operation, that is equal to complement of A ANDed with complement of B, and the complement of AND operation, that is equal to complement of A ORed with complement of B. Or in simple terms we can remember this as break the line and change the sign. Like here we have complement, whole complement, that we break to the individual variable. This is whole complement that we break to the individual variable. We take complement of A and complement of B individually, and instead of plus sign we put here dot sign. So we can say break the line and change the sign. If it is plus, put it dot, and this line is break, that means whole complement is break into two parts, that is A complement and B complement. Same way here we have complement of product, that is equal to product is dot is changed to plus. So change the sign and break the line, A complement plus B complement. So how to verify it? We take A and B with the four combinations 0 0 0 1 1 0 and 1 1. Here we take A plus B by ORing these two. Then we take A plus B to the complement by complementing this column. Then here we take A complement, complement of this. Here we take B complement, complement of this. Here we take ANDing of these two, that is A complement ANDed with B complement. Then we take A and B, and then we take A and B to the complement, and finally we take A complement plus B complement. So we match that A plus B to the whole complement, that is equal to A complement dot B complement. This column and this column is matching. So we have proved this theorem that complement of sum is equal to product of individual complements. And here we see A dot B to the whole complement. So A dot B to the whole complement. So here we have 1 1 1 0, and here we see A complement plus B complement, that is again 1 1 1 0. So these two columns are matching. So this is a proof of this theorem, that is complement of product is equal to sum of individual complements. So these are the references I have used. Thank you.